Tonight, we are following a single question out into the dark. If we left Earth in 2026 and aimed for the nearest star beyond the Sun, how long would it really take to get there? By the end of the night, you will know the answer in years, but you will also understand what those years actually mean, how far the next star truly is, how fast we can really travel, and what kind of world might still be here by the time any message finally comes home. When people look up at the night sky, the stars can feel almost gathered together. They fill the darkness so completely that the sky seems crowded. One point of light sits near another. A bright star glows over a roofline. A faint one waits higher above it. They look as though they belong to the same distant surface, almost like lanterns pinned into a ceiling far above the Earth. But space does something strange to human sight. It hides depth. A star can appear beside another star and still be separated from it by distances so large that the human mind has no natural way to hold them. The sky is full, and yet the space inside it is mostly empty. It is an emptiness so wide that even the nearest star beyond our own sun lives at a distance that changes the meaning of travel itself. That is where tonight's question begins. If we left in 2026, how long would it take to reach the next star? At first, it sounds like the kind of question that should have a clean answer. A number, a calculation, a destination, a speed, and a result. The kind of answer you could write down in a line or two and move on from. But some questions only look simple from a distance. As soon as you walk toward them, they begin to open. This is one of those questions. Because the moment we ask how long it would take, we also have to ask where we are going. We have to ask what counts as leaving. We have to ask how fast human beings can actually move through space. We have to ask whether a journey can still feel like a journey when it lasts longer than a lifetime, longer than a civilization, longer than most of recorded human history. And somewhere deeper inside the same question is another one, waiting quietly. What does it mean to begin a trip that you already know you will never see completed? That is part of why the next star has such a hold on human thought. It sits close enough to be named and far enough to remain almost beyond feeling. It is near in astronomical terms. It is impossibly far in human terms. Those two truths live side by side, and the tension between them gives this question its weight. For most of human history, the stars were lights first. They were markers, stories, patterns, and signs. They helped people navigate seas and seasons. They gave shape to myths. They offered company to lonely nights. Only later did they begin to change in the human imagination. They became suns, real places, distant fires. Other worlds may circle them. Other skies may exist beneath them. And once that shift happened, one quiet idea began to follow. If those stars are real places, could anything from Earth ever reach one? Tonight, we are beginning with the nearest one, not the brightest one in our sky, not the most famous, the nearest, the first star beyond the sun that stands as the smallest possible step into interstellar space. And even that smallest possible step will ask more of distance, time, engineering, and patience than almost any journey human beings have ever imagined. So before we talk about spacecraft, before we compare speeds, before we place human machines against the scale of the dark, we need to do something simpler. We need to bring the destination into view. Because the next star is more than a phrase. It has a name. It has a place. It has a distance that can be measured. And once that distance is spoken aloud, the whole shape of this question begins to change. The answer does exist. It can be calculated. But its meaning only begins to settle in once we know which star is waiting there, just beyond the edge of the sun's long neighborhood, as the first true destination beyond home. The question has now narrowed into something more concrete. A journey always changes once the destination stops being an idea and becomes a real place with a real name. The first name that matters here is Proxima Centauri. When people say the next star, they are usually imagining something simple. A single bright light just beyond the sun, waiting out there as the nearest stop in the wider dark. The truth is a little more textured than that, and somehow more interesting because of it. Proxima Centauri is the nearest known star beyond our sun. It lies about 4.25 light-years from Earth, which comes out to about 40.2 trillion kilometers. That distance alone begins to reshape the whole video, because once the destination is fixed, the question becomes harder, clearer, and more physical. We are no longer asking about stars in a poetic sense. We are asking about one specific star at one measured distance, sitting at the edge of the sun's neighborhood. Proxima is part of the Alpha Centauri system, which is a triple star system. The two brighter members are Alpha Centauri A and Alpha Centauri B. Those two orbit one another and sit slightly farther away from us, at about 4.35 light-years. Proxima is the smaller companion, a dim dwarf star associated with that same family. So the nearest star beyond the sun is not the brightest one in that nearby system. It is the quieter one, the smaller one, the one that would be easiest to overlook if human eyes could somehow see the true structure of the scene all at once. There is something fitting about that. The first star beyond home is not a grand lantern blazing in the dark. It is a red dwarf, faint and modest, holding the strange honor of being the closest. In the sky, that closeness does not feel obvious. The sky is very good at hiding real depth. It spreads stars across a black surface and lets them seem almost equally far away, as though they all belong to one distant ceiling. But space is not arranged like a ceiling. It is arranged like an immense volume, and the stars are scattered through it at distances so great that even the nearest one can remain almost beyond feeling. That is part of why naming Proxima matters. A name makes the journey more real. It takes the viewer from a vague thought into a measured reality. The next star is not just a concept now. It is Proxima Centauri. It has companions. It has a place in a nearby stellar system. It has a known distance that astronomers can write down. The moment those facts settle in, the word near begins to change. Near in astronomy carries a very different kind of meaning than near in ordinary life. In ordinary life, near means across the street, down the road, maybe across town. In the solar system, near already begins to stretch. Mars can be called near and still sit tens of millions of kilometers away. But among the stars, near becomes almost abstract. The research describes Proxima's distance as roughly 268,770 times the distance between Earth and the Sun. That is an enormous multiplication of a span that already shapes every day of life on Earth. The sunlight that reaches your room, the warmth on the ground, the turning of the seasons, all of it happens across that one familiar Earth-Sun distance. To stretch that distance more than 268,000 times is to enter a scale that the human mind does not naturally carry around. And still, that is the nearest star. That is one of the quiet shocks at the heart of this whole subject. The stars look abundant. They fill the sky. They can seem almost pressed together on a winter night. Yet the space between them is so wide that even the closest one remains separated from us by a gulf that light itself needs 4.25 years to cross. Light moves faster than anything else in the universe that we know how to measure, and even light does not arrive quickly from Proxima. So this is the first real anchor point in the journey. If we left in 2026, this is where we would be trying to go. Not toward a general patch of stars, not toward a bright idea in the sky, toward Proxima Centauri, the nearest star beyond the Sun, small and faint and still unimaginably far away. Once that destination is fully in view, the next step becomes unavoidable. We have to sit with the unit that measures such a distance, because a light year is easy to say and much harder to feel. Now the destination has a name, and the next thing that needs to come into focus is the unit that carries so much of this story. A light year is easy to say. It is much harder to feel. A light year is a measure of distance. It is the distance light travels in 1 year, about 9.46 trillion kilometers. That means Proxima Centauri, at about 4.25 light years away, sits roughly 40 trillion kilometers from Earth. Those are the numbers, and they are already large enough to feel almost detached from ordinary life. But this is where the real work of understanding begins, because a number that large can pass through the mind without leaving much behind. Human beings are good at feeling small distances. A room makes sense. A road makes sense. Even a country, though large, can still be pictured in fragments. You can imagine crossing it in days or flying over it in hours. The same is true, in a different way, for distances inside the solar system. Once they are explained slowly enough, they may feel enormous, but they still belong to a world where movement seems possible. A spacecraft can cross the distance to the Moon in days. Mars can be reached in months. Even the outer planets, though they demand patience, still belong to a framework the human mind can gently stretch itself around. A light year changes that. The word itself sounds almost soft. It has the brightness of light in it. It has the rhythm of a year in it. Put together, it can seem almost graceful. But what it contains is severe distance. It means that even light, the fastest thing nature allows, needs a full year to cover that span. The nearest star beyond the Sun is more than 4 of those years away, even for light itself. So when a person hears that Proxima Centauri is 4.25 light years from Earth, the deeper meaning is this: even the fastest thing in the universe does not arrive quickly. That is where the human analogies begin to help. The research for this video gives a few very calm comparisons. A car moving at 100 kilometers per hour would need more than 45 million years to drive that far. A jet moving at about 900 kilometers per hour would still need around 5 million years. Those are not travel times in any ordinary sense. They are longer than human civilization, longer than written language, longer than almost everything a person naturally uses to measure time. The comparisons are useful because they do not make the distance smaller. They simply let the viewer feel how completely ordinary movement fails once the stars are involved. And that failure is important to sit with for a moment, because this is where a common illusion starts to fade. The night sky gives the impression of closeness. The stars seem sprinkled across one surface. A bright one here, a faint one there. The gaps between them look small because the eye is only seeing directions, not true depth. A light year is one of the first units that restores that missing depth. It tells us that stars are not hanging side by side above us, like points on a ceiling. They are scattered through an enormous three-dimensional dark, each one separated from the others by gulfs that can swallow entire human histories. That is why the nearest star already feels so extreme. If even the first step beyond the sun is measured in light years, then the scale of interstellar travel is revealed before any spacecraft has even launched. The journey is difficult before engineering enters the picture. It is difficult the moment the distance is honestly described. In that sense, the light year is doing more than measuring space. It is also measuring the limits of human intuition. It is showing the viewer where everyday feeling stops being enough, and where a slower kind of understanding has to take over. There is also something quietly humbling in the way this unit works. Human beings created roads, maps, clocks, ships, and aircraft. We filled the earth with ways of crossing distance, but the light year comes from something far older than us. It comes from the speed of light itself, from the behavior of the universe before any human being ever looked up and wondered what the stars were. We did not invent this scale. We discovered that it was already there, waiting to rearrange our sense of nearness. So by this point in the journey, the title question has already become heavier. If we left in 2026, how long would it take to reach the next star? The answer cannot just come from naming Proxima Centauri. It cannot just come from saying 4.25 light years. Now the question needs motion. It needs speed. It needs a comparison between the scale of the road ahead and the fastest things human beings have ever managed to send into the dark. That is where the next part of the story begins. Now the distance has been named, and the next part of the question becomes more physical. What would it actually mean to leave in 2026? A launch date can sound very clean when it is spoken out loud. It can make the whole idea feel as if a spacecraft simply rises from Earth, points itself toward Proxima Centauri, and begins the long crossing at once. Real motion through space is quieter and more layered than that. A mission leaving in 2026 would begin with fire, timing, and gravity. Before it could travel toward another star, it would first have to leave the deep motions of home behind. The first step would be leaving Earth itself. That sounds obvious, though it already holds a large amount of effort inside it. Earth is not only a place. It is also a mass, and mass holds things close. To rise from the surface and keep going, a spacecraft has to reach space with a rocket powerful enough to break free of the planet's pull. Earth's escape velocity is about 11.2 kilometers per second. That number is one of the first gates in the journey. Until it is crossed, there is no road to another star at all. But escaping Earth is still only the beginning. Earth is moving around the Sun at about 30 kilometers per second. That means any spacecraft leaving Earth is already born inside a larger motion. It is not sitting still in space waiting to choose a direction. It is already circling the Sun with the planet that launched it. To truly set out for the stars, the spacecraft would also have to escape the Sun's gravitational hold. And the research notes that from Earth's orbit, this calls for roughly 12 kilometers per second, beyond Earth's orbital motion. So even after a rocket has climbed away from Earth, there is still a second, wider act of departure taking shape around it. This is part of what makes interstellar travel feel different from ordinary travel. A person leaving one city for another does not first need to escape the city, then the country, then the continent, then the motion of the ground under their feet. In space, leaving is nested. One layer sits inside another. A mission begins inside Earth's gravity, inside Earth's orbit, inside the Sun's far wider domain. To say we left in 2026 is to say we began the long task of slipping outward through all of those layers. That would likely require more than one burn of one engine. The research describes a realistic mission as something that would probably use a strong launch rocket to reach orbit, then further stages or gravity assists to build solar escape speed. That means the journey to another star would begin with a chain of help. A launch vehicle would lift the probe away from Earth. Upper stages might add more speed. A flyby of Jupiter or Saturn could lend still more momentum. Human missions already do this inside the solar system, quietly borrowing motion where they can. A star mission launched with present-day methods would almost certainly do the same. Even then, a spacecraft leaving in 2026 would spend a long time still surrounded by the architecture of the solar system. It would move outward past the planets and into the outer regions shaped by the Sun. The research points to the Kuiper Belt, stretching roughly from 30 to 50 astronomical units, and then farther on to the heliosphere, the broad bubble of solar influence that extends to about 121 astronomical units. Voyager 1, which is often used as the emotional benchmark for this whole subject, took more than 35 years to reach the heliopause, the place where that bubble gives way to true interstellar space. That one detail quietly changes the title question again. A mission can leave Earth in 2026 and still spend decades only finishing its departure from the Sun's wider neighborhood. That is worth pausing on. When people imagine travel to another star, the mind often leaps straight to the star itself. But the first real chapter of such a mission would still be about the solar system, about climbing out of the well, about carrying enough speed to keep going, about passing the planets, then the darker reaches beyond them, then the long boundary where the Sun finally thins into the larger medium between stars. The departure would not feel like a sudden break. It would feel like a slow fading of home. And that slow fading matters because it gives shape to the word leave. Leaving in 2026 would not mean beginning the star crossing in any intimate sense. It would mean beginning the long escape. The first outward chapter. The part where human engineering tries to turn one planet-bound species into something that can at least start moving between suns. Once that act of departure is understood, another question begins waiting beside it. If we could truly leave, how fast could we go once we were on our way? Now the question becomes simpler in one way and much harder in another. If a spacecraft really did leave Earth and begin the long outward climb, how fast could it actually go? This is where human ambition meets one of its clearest limits. We know how to build machines that move at astonishing speed compared with anything on Earth. We know how to send probes past planets, out through the cold edge of the solar system, and into regions no human being will ever physically touch. But the stars force a more honest comparison. They do not care how fast something feels to us. They only care how much distance remains. One of the most useful spacecraft to think about here is Voyager 1. It has been traveling away from the Sun for decades, moving at about 17 kilometers per second. That is an extraordinary speed by human standards. At that pace, it could cross a continent in minutes. It could circle Earth in far less than an hour if it flew low enough through the atmosphere, which of course it cannot. It is already farther from Earth than anything human beings have ever made. And yet, against the distance to the nearest star, even Voyager begins to feel slow. That is one of the strange emotional turns in this story. A machine can be one of the greatest outward achievements in the history of our species, and still seem almost still when placed beside interstellar distance. Then there is New Horizons, another fast traveler. It left Earth at one of the highest launch speeds ever achieved by a human-made object, later gaining even more motion from Jupiter. It crossed the solar system with a kind of quiet elegance, reached Pluto, and kept going. In most stories of space exploration, that is more than enough to earn the word fast. And it is fast. It is fast enough to make the planets feel like connected places in one shared system. But once the destination becomes a star, even that speed stops feeling like true reach and starts feeling more like a beginning. And then there is Parker Solar Probe, which pushes this question into even sharper light. Parker has reached the highest speed ever recorded by a human spacecraft, about 700,000 kilometers per hour, which is about 191 kilometers per second. That number is so large it almost seems like the answer humanity has been waiting for. At first hearing, it sounds as though the problem may already be solved. If we can move that fast, then perhaps the stars have already begun to come within range. But Parker's speed comes with an important kind of silence around it. It reaches that speed only by diving extremely close to the Sun. It is not cruising outward through interstellar space at that pace. It is falling deep into the Sun's gravity well and racing through the most intense part of that path. In other words, it is a peak speed, not a sustained starbound speed. That difference matters. It matters because the stars do not reward brief moments of velocity. They reward long, relentless crossing. Still, Parker tells us something important. It tells us what human engineering can do when it is pushed to an extreme. It tells us that our machines can already touch speeds that would have sounded impossible not very long ago. And even then, the nearest star remains distant enough to humble that achievement. This is where the human mind begins to split the word fast into two meanings. There is fast in the ordinary sense, and there is fast enough for the stars. Humanity already knows the first kind. We have built it. We have launched it. We have watched it race through the dark. But the second kind is something else entirely. It belongs to a deeper category of motion, one where even our greatest machines are still moving at only tiny fractions of the speed of light. Voyager, New Horizons, and Parker Solar Probe are not failures because they fall short of interstellar travel. They are reminders of where the real threshold begins. And that threshold is much farther out than most instincts expect. Because once the nearest star is placed beside the fastest machines we have ever built, a harder truth begins to settle in. The question is no longer whether human beings can move quickly through space. We clearly can. The question is whether our current speeds are enough to make another star feel reachable in anything like a human timescale. That is the point where speed turns into time, and where the title of this video finally starts asking for real numbers rather than just awe. The first truly hard answer comes from a spacecraft that is already on its way outward. Voyager 1 gives this question a sharper edge because it is not a fantasy machine, and it is not a concept sketched on paper. It is real. It was launched by human beings. It has traveled for decades. And even with all of that behind it, the nearest star remains almost impossibly far away. Voyager 1 is moving away from the Sun at about 17 kilometers per second. That is an astonishing speed by any ordinary measure. It is faster than a rifle bullet, faster than anything people ever experience in daily life. It has already crossed the boundary into interstellar space and become the most distant human-made object ever sent outward. In one sense, it is exactly the kind of machine that makes a question like this feel possible. If humanity has already built something that can leave the deep neighborhood of the planets, then it makes sense to ask how long such a machine would take to continue all the way to the nearest star. And that is where the feeling changes. At Voyager 1's speed, the trip to Proxima Centauri would take roughly 73,000 years. That number is so large that it barely arrives all at once. It does not land like a normal travel time. It lands more like geology, more like the age of ancient landscapes, more like a stretch of time in which whole human worlds could appear, change, and disappear. A journey measured in 73,000 years no longer feels like an expedition in the way people usually use that word. It feels like something larger than any crew, larger than any nation, even larger than the civilization that began it. To feel that number more clearly, it helps to set it beside human history. 73,000 years ago, there were no cities, no writing, no metal tools, no libraries, no ships crossing oceans under maps and flags. Agriculture had not yet reshaped the land. Kingdoms had not risen and fallen. Most of what people think of as history still lay far in the future. Human beings were alive, of course, but the worlds they inhabited were separated from ours by an almost unimaginable span of cultural change. That means a Voyager speed mission to the nearest star would take longer than the entire history of civilization many times over. Ancient Egypt would fit comfortably inside that span. So would classical Greece, Imperial Rome, the medieval world, the rise of modern science, the industrial age, the digital age, and whatever comes after it. Entire chains of empire, language, religion, architecture, and technology could rise and pass away, while the spacecraft continued moving through the dark at the same quiet speed. That is part of what makes this such a sobering benchmark. Voyager 1 is not slow in any human sense. It is only slow in the presence of the stars. And this changes the emotional meaning of departure. If a probe left Earth in 2026 at Voyager-like speed, no one alive at launch would ever see it arrive. Their children would not see it. Their grandchildren would not see it. Thousands of generations could pass before the crossing ended. Even the idea of family becomes too small to hold a journey like that. What begins as a mission starts to resemble a message placed into time itself. It also means that the institution launching it would almost certainly not survive unchanged. The governments involved might not exist in recognizable form. The language used to design the craft might evolve beyond easy recognition. The reasons for launching it could become distant memory, then myth, then maybe even nothing at all. A spacecraft traveling for 73,000 years would move through time as much as space. It would outlast policies, agencies, borders, currencies, and probably whole ways of organizing society. And yet there is something strangely beautiful in that too. A mission of that length would be one of the clearest examples of humanity doing something it knows it will never personally complete. It would be an act of continuity rather than possession. The people who launched it would be offering the future a beginning, not an ending. They would be saying that some journeys matter even when arrival belongs to minds and cultures not yet born. Still, the number remains severe. 73,000 years is not a difficult wait. It is a transformation of the entire meaning of travel. At that point, reaching the next star with current outward spacecraft speeds no longer feels like a matter of patience alone. It feels like a limit being revealed. It shows that humanity can begin the journey, but not yet in a way that keeps it close to human life. Voyager 1 gives the title question its first real answer, and that answer is both honest and humbling. If we left in 2026 using the kind of outward speed Voyager carries now, the nearest star would not be reached in centuries or even millennia. But in a span of time so long that almost everything familiar to us would be gone before the destination was ever touched. And once that answer is heard, another question rises almost immediately. If this is what one of our great outward spacecraft can do, what happens if we stop using a decades-old benchmark and instead look at the fastest speed any human machine has ever reached at all? There is another number that changes the feeling of this question the moment it enters the room. Voyager 1 gives us a real outward speed, and the answer it produces is severe enough on its own. But then Parker's solar probe appears with a much more dramatic figure. At its fastest, Parker has reached about 700,000 kilometers per hour, which is about 191 kilometers per second. That is the highest speed ever reached by a human-made spacecraft. The number is so large that it seems for a moment like it should reopen the whole conversation. Maybe this is the speed that finally begins to make the stars feel less impossible. Maybe this is where the long silence between suns starts to shrink. And in one sense, it does change things. Compared with Voyager 1, Parker's peak speed is enormous. Voyager moves outward at about 17 kilometers per second. Parker, at its fastest, is moving more than 11 times faster than that. When people first hear a comparison like that, the instinct is to imagine the travel time collapsing. If one of our spacecraft can move more than 10 times faster than Voyager, then surely the nearest star begins to slide out of the realm of tens of thousands of years and into something more manageable. But this is where space quietly keeps its advantage. Even if Parker's top speed could somehow be held continuously all the way to Proxima Centauri, the trip would still take about 6,700 years. That number is vastly smaller than 73,000 years. It is a huge improvement. It is the difference between a journey longer than most of human prehistory and a journey longer than nearly all of recorded civilization. But it is still a journey so long that no ordinary human category can comfortably contain it. That is the strange thing Parker reveals. You can increase the speed by an extraordinary amount and still remain trapped inside deep time. 6,700 years is not a mission in the everyday sense. It is longer than the age of the pyramids, longer than the oldest cities still remembered by name, longer than most religions in their present form. If a probe left Earth in 2026 and somehow held Parker's greatest speed the whole way, the world receiving the news of its arrival would be separated from ours by spans of change almost too large to imagine clearly. Languages would shift, nations would pass, entire traditions of thought could fade, divide, merge, or disappear. The launch itself might survive only as a fragment of deep historical memory, and yet, even this thought experiment is gentler than reality. Because Parker's solar probe does not travel outward through the solar system at 191 kilometers per second as a steady cruising speed, that number comes from a very special kind of motion. Parker reaches it when it dives extremely close to the Sun, falling inward through the Sun's gravity and whipping around at astonishing speed near perihelion. Its record-breaking motion is tied to that deep solar plunge. It is not the same thing as aiming a spacecraft toward another star and maintaining that speed for thousands of years. That distinction matters because peak speed and useful interstellar speed are not the same kind of achievement. A stone dropped into a valley can move quickly for a moment, but that does not mean it can cross a continent. Parker's record shows what human engineering can do in a very particular gravitational setting. It shows that we can build machines able to withstand the Sun's fierce environment and reach astonishing velocities under the right conditions. But the stars ask a different question. They do not ask how fast a spacecraft can move for a brief moment under extreme circumstances. They ask how fast it can move steadily, usefully, and with direction across trillions of kilometers of emptiness. And that is where the emotional force of Parker's number really lives. It gives us hope for a moment, and then it teaches scale all over again. Because 700,000 kilometers per hour sounds like the kind of speed that should erase the problem. It sounds almost unreal in a human context. Across Earth, it would turn cities into instants, continents into short crossings. The globe itself would become something you could circle in moments. But the nearest star does not care how astonishing that speed feels on Earth. It only cares that even this record-setting motion remains tiny beside the road ahead. That is one of the most important shifts in the whole video. The question stops being whether humanity can build fast machines. Clearly, it can. The question becomes whether human definitions of fast are anywhere close to what interstellar space requires. Parker gives the clearest answer so far. It says that even the fastest speed ever reached by one of our spacecraft still leaves us with a journey measured in thousands of years. And that is only if we imagine maintaining a condition that the spacecraft itself does not actually sustain. So Parker does not solve the problem. It sharpens it. It shows that the stars are not merely far in the way mountains are far, or oceans are far, or even outer planets are far. They are far enough to swallow even our most dramatic speeds and return them to us as long ages. It is one thing to hear that another star is 4.25 light years away. It is another thing to watch that number absorb humanity's fastest machine and still answer back with nearly 7 millennia. By this point, the real shape of the challenge begins to emerge more clearly. Travel between stars is no longer starting to feel like a transportation problem in the usual sense. It is becoming something deeper and stranger. It is becoming a problem of time. A trip across a city is measured in minutes. A trip across a country is measured in hours. A trip across an ocean is measured in days. A trip across the solar system begins to stretch into years. But a trip to another star moves into a different category altogether. It begins to be measured in eras. That shift matters because it changes the meaning of travel itself. Once a journey grows beyond a human lifetime, it no longer feels like movement in the ordinary sense. It becomes something harder to describe. The word trip starts to feel too small. Even the word mission begins to thin out. A person can imagine boarding something, waiting, and arriving. That is how human travel usually works. There is a traveler, a passage, and an end. But interstellar distance starts to dissolve that shape. The traveler may never see the destination. The people who built the craft may never know what became of it. The culture that launched it may not survive long enough to receive the answer. That is why time and distance cannot really be separated in this story. The nearest star is far away in kilometers, but what that distance really does is turn itself into time. It changes speed into waiting. It changes engineering into continuity. It changes one launch into a relationship between different generations of people who may never meet, never share a language, and never fully share the same world. At that point, another star no longer feels like a place you simply go. It begins to feel like a horizon that is carried forward through history. That is one of the deepest differences between interstellar travel and almost every other form of travel human beings have ever known. When a ship crossed an ocean in the past, the people who left were still part of the same human moment as the people who arrived. They may have crossed into a different land, but they belong to the same age. Even long sea voyages still fit inside a lifetime. Even the earliest space missions to the moon, though dangerous and difficult, still belong to the same living frame of memory as the societies that sent them. But once the travel time becomes centuries, millennia, or longer, the journey itself begins to outlast the moment that created it. A spacecraft can then become almost like an artifact in motion. It leaves one world and arrives in another, not only because it crosses space, but because time changes everything around it while it travels. A probe launched in one age might arrive in an age with different languages, different political structures, different beliefs about the universe. Perhaps even different kinds of human beings shaped by technology, biology, or long civilizational change. In that sense, interstellar travel is never only a journey outward. It is also a journey forward through human time. And that is where the true obstacle starts to look different. At first, the problem seems to be propulsion. Build a stronger rocket, find a denser fuel, discover a better engine. Those are real problems, and they matter deeply. But the farther the star remains, the more another challenge begins to stand beside them. The challenge is continuity. How do you begin something that may only matter fully to people not yet born? How do you preserve purpose across time? How do you keep knowledge, meaning, and memory intact long enough for a journey to remain understandable? That question applies even to an unmanned probe. A robotic craft does not need food, air, or comfort, but it still needs a world behind it that can remember what it is doing. It still needs institutions, archives, methods of communication, and a line of attention stretching across generations. Without that, even a successful mission could become strangely disconnected from the civilization that began it. The spacecraft might continue faithfully outward, while the reasons for sending it slowly blur back on Earth. And if human beings were ever placed on board, the meaning of travel would change even more. Then the journey would not only connect generations, it would contain them. Children might be born into the mission, adults might live and die without seeing anything except the vessel and the dark outside it. Home would stop being a place behind them and become a memory preserved in stories, images, rituals, and inherited knowledge. The ship would no longer be just a machine. It would become a moving world. That is why interstellar travel asks for more than motion. It asks what kind of species human beings are willing to become in order to cross such distances. It asks whether curiosity can remain stable across ages. It asks whether a journey can still be called a journey when the beginning and the end belong to different chapters of civilization. And once that begins to settle in, another quiet truth becomes stronger. Another star does not begin where the solar system ends in imagination. It begins where the solar system ends in reality. And that reality is much larger, slower, and more gradual than the mind first expects. Even after a spacecraft leaves Earth, it does not immediately enter the space between stars. For a long time, it is still inside something larger. It is still inside the reach of the sun. Home does not end at the edge of the atmosphere, or even at the orbit of the farthest planet. It fades slowly. It stretches outward in layers, each one thinner than the last, until it finally gives way to the wider dark between stars. To understand what it means to travel to another star, it helps to see how long it actually takes just to leave this extended neighborhood behind. The first of these outer regions is the Kuiper Belt. Beyond the orbit of Neptune, beginning at about 30 times the distance between Earth and the Sun, there is a wide region filled with icy bodies. These are remnants from the early solar system, objects that never became full planets. Pluto is one of the most well-known members of this distant zone, but it is only one among many. The Kuiper Belt stretches outward to roughly 50 astronomical units, forming a broad, quiet band of debris and frozen worlds. A spacecraft heading for another star would pass through this region as part of its early outward journey, still very much inside the structure of the solar system. Beyond the Kuiper Belt, the Sun's influence continues. It does not stop at the last planet or the last cluster of icy objects. Instead, it extends outward as a vast bubble known as the heliosphere. This bubble is formed by the solar wind, a constant flow of charged particles streaming away from the Sun in all directions. It pushes outward against the surrounding interstellar medium, carving out a region of space where the Sun's presence is still dominant, even at great distances. This heliosphere is enormous. It reaches far beyond what the eye or instinct might expect. At its outer edge lies the heliopause, the boundary where the outward pressure of the solar wind balances against the particles of interstellar space. Crossing that boundary is not a sudden leap into emptiness. It is more like passing from one kind of environment into another, where the Sun's influence becomes less direct and the wider galaxy begins to take over. Voyager 1 crossed that boundary at a distance of about 121 astronomical units from the Sun. It took more than 35 years to reach that point. That single fact quietly reshapes the idea of departure. A spacecraft can leave Earth, pass the planets, and still spend decades just reaching the edge of the Sun's extended domain. For all that time, it is still, in a meaningful sense, part of the solar system. It is still moving through a region shaped by the Sun, still within a structure that belongs to home. Only after that long outward passage does it begin to move through what can truly be called interstellar space. Even then, the transition is not absolute. The interstellar medium itself is not empty. It is filled with thin gas, dust, and fields that drift between the stars. The spacecraft does not suddenly enter a clean void. It enters a different kind of environment, one shaped less by the sun and more by the broader structure of the galaxy. The journey continues, but the background has changed. What matters here is the scale of that first step. Before a spacecraft can even begin the long crossing toward another star, it must first complete this slow exit from the sun's wide and subtle influence. That exit alone takes decades at the speeds we currently achieve. It is not a brief prologue. It is a full chapter of the journey, one that unfolds quietly as the familiar markers of the solar system fall farther and farther behind. The planets disappear into distance. The sun itself begins to shrink, no longer a dominant presence but a bright star among many. The environment around the spacecraft shifts, gradually and without ceremony, from something shaped by our local star to something shaped by the wider galaxy. That is when the journey truly begins to feel interstellar. Not at launch, not at orbit, not even at the edge of the planets, but out there, far beyond the last major structures of the solar system, where the sun's influence thins and the space between stars becomes the dominant reality. And once that long departure is understood, another question begins to take shape. If it takes decades just to leave the sun's wider neighborhood at current speeds, why is it that the same rockets that can carry us this far still leave the stars so far out of reach? The engines that carried humanity off the Earth are among the most powerful machines ever built. They changed history. They opened the planets. They made the moon a real destination and turned the outer solar system into something we could touch with instruments and cameras. But they also live inside an old rule of physics that quietly limits what they can do. A rocket works by throwing mass backward so that the spacecraft moves forward. That is the basic exchange. Hot gas rushes out one way and the vehicle is pushed the other way. It is simple in principle, and it has carried human technology from launch pads into deep space. But the difficulty begins the moment a mission asks for far more speed, because the fuel needed to gain that speed also has weight, and that weight must be pushed too. This is where the problem starts to fold in on itself. If you want a rocket to go faster, one obvious answer is to give it more fuel. But more fuel means more mass. And more mass means the rocket needs even more energy just to move the added fuel it is carrying. So a large part of the rocket's effort is spent accelerating the very thing meant to help it accelerate. That is the quiet trap hidden inside chemical propulsion. The faster you want to go, the more severe the burden becomes. At first, this works well enough. It is why multi-stage rockets exist. One tank empties, falls away, and allows the remaining vehicle to keep moving with less dead weight. This is a clever and powerful solution, and it has made modern spaceflight possible. But even staging only stretches the reach of chemical rockets so far. It helps them leave Earth. It helps them cross the solar system. It does not transform them into star machines. The reason is that chemical rockets simply do not throw their exhaust out fast enough. Their exhaust speeds are impressive in human terms, but interstellar distance is not measured against human terms. It is measured against the speed of light, against trillions of kilometers, against journeys that must somehow avoid turning into millennia. To reach another star in anything like a meaningful span, a spacecraft would need far greater speed than chemical propulsion can reasonably provide. And because the fuel mass grows so punishingly as the desired speed rises, the rocket begins to demand absurd proportions of itself. A star-bound chemical rocket would not just need more fuel. It would need such an enormous amount that the vehicle would begin to look less like a spacecraft and more like a moving pile of propellant, with a very small mission hidden somewhere at the top. That is the emotional turning point here. The rockets that feel mighty on Earth begin to look fragile when placed beside the distance between stars. It is not because they are poor inventions. It is because they were born for a different scale of travel. They are the right tools for lifting away from a planet and moving through a solar neighborhood. They are not the right tools for swallowing light years. This helps explain why the nearest star still feels so unreachable even after a century of astonishing progress in flight. Humanity did not fail to build good rockets. Humanity built rockets suited to the worlds immediately around it. That alone was a breathtaking achievement. But another star belongs to a harsher category of distance, one where even excellent tools begin to show the boundaries of their design. So when people imagine a spacecraft simply carrying enough fuel to keep pushing all the way to Proxima Centauri, the picture sounds easier than the physics allows. Each increase in speed comes at a growing cost. Each extra gain becomes more expensive than the last. The rocket is always paying for its own fuel by hauling that fuel along. Eventually, the balance becomes brutal. The mission spends too much of itself just preparing to move a little faster. That is why chemical rockets remain wonderful and limited at the same time. They are wonderful because they work. They have already done what earlier ages would have called impossible. They have carried human beings beyond the atmosphere, sent probes to every major planet, and pushed machines into interstellar space. But they are limited because the stars ask for something beyond brute extension of the same method. They ask for a deeper change in how motion is produced. Once that becomes clear, human thought begins to wander in a different direction. If ordinary rockets cannot bridge the gulf, then perhaps speed must be borrowed more cleverly, or created by stranger engines, or driven by forms of energy far denser than chemical fire ever allowed. Before people began imagining entirely new kinds of engines, spaceflight learned something quieter and more elegant. A spacecraft does not always have to earn every bit of its speed alone. Sometimes motion can be borrowed. This is one of the most beautiful ideas in all of orbital mechanics. A planet is not just a place in space. It is also a moving mass, carrying enormous momentum as it circles the sun. If a spacecraft approaches that planet along the right path, at the right angle, and at the right time, it can leave with a different amount of speed than it had before. The planet loses a tiny amount of its own motion, far too little to notice, and the spacecraft gains a useful push. This is called a gravity assist. It can sound almost magical when first described, but it is really a kind of exchange. The spacecraft falls into a planet's gravity well, curves around it, and departs in a new direction. Relative to the planet, it may leave with nearly the same speed it arrived with. But relative to the Sun, the result can be very different. By approaching a moving planet in the right way, the spacecraft can take a small share of that planet's orbital momentum and carry it onward into deeper space. Human spaceflight has already used this trick to great effect. Voyager 1 is one of the clearest examples. Its outward path was helped by flybys of Jupiter and Saturn. Those giant planets did not merely serve as scenery or checkpoints. They helped shape the mission's speed and direction. flinging the spacecraft farther outward than its rocket alone could have managed. This is part of why Voyager became such a powerful symbol of humanity's reach. It was not only a triumph of engineering on the launch pad, it was also a triumph of geometry, timing, and patience. The solar system itself helped send it on its way. New Horizons offers another beautiful case. It launched with extraordinary speed already, then used a flyby of Jupiter to gain even more momentum. That borrowed motion shortened its travel time to Pluto and helped carry it deeper into the outer solar system. Without Jupiter, the mission would still have worked, but the story of its speed would have been less elegant, and the crossing would have taken longer. In a very real sense, the largest planet in the solar system helped open the road. That is what makes gravity assists feel so graceful. They reveal that space travel is not always a matter of overpowering distance. Sometimes it is a matter of understanding the dance already taking place and slipping into it wisely. And yet, even here, the stars remain severe. A gravity assist can add meaningful speed. It can reshape a mission. It can turn a difficult planetary voyage into a practical one. But on interstellar scales, these boosts are still modest. A few kilometers per second matter greatly when traveling to Jupiter, Saturn, Pluto, or beyond. They do not erase the gulf between the Sun and Proxima Centauri. They help, but they do not transform a star journey into something intimate or short. This is one of the recurring lessons in the whole question. Human cleverness keeps finding real advantages. The universe keeps answering with scale. There are other limits too. Gravity assists are not available anywhere and anytime in whatever form we wish. They depend on the arrangement of planets, their positions in orbit, and the exact path a mission can take. A good assist is not simply turned on like an engine. It is something planned around a moving solar architecture. That means every mission must work with what the solar system is offering at the moment of launch. Even giant planets can only lend so much, and only under the right circumstances. So gravity assists are powerful, but they are still part of the solar system's logic, not an escape from it. They belong to a style of travel in which planets are used as stepping stones, slings, and guides. That is perfect for missions within the Sun's family of worlds. It is one of the reasons humanity has been able to move so effectively across such large planetary distances. But the road to another star eventually stretches beyond the reach of helpful flybys. Once the last useful planet is behind you, borrowed motion ends, and whatever speed you carry then becomes the speed you must live with for the long crossing. That is the quiet boundary gravity assists reveal. They show how far intelligence can stretch the tools we already have. They show that motion can sometimes be found rather than merely forced. But they also show that there comes a point where clever routing is no longer enough. Past that point, the question changes. It is no longer how to use the solar system more skillfully. It becomes how to move through interstellar space with an entirely different level of power. And once that question arrives, human thought begins to turn toward engines and ideas that sound much stranger than ordinary rockets. Because if borrowed motion is still too small, then the next step is to ask what forms of propulsion might truly begin to shrink these travel times. When people began imagining travel to another star in a serious way, they reached almost immediately for a deeper kind of fire. Chemical rockets had already shown what they could do. They could lift machines away from Earth, send people to the moon, and push probes past the planets. But once the destination became another sun, the old fuel began to feel too thin. The gap was simply too large. The speeds required were too high. So the search moved toward energy sources far denser than chemical flame, sources that could release much more power from much less mass. That is where nuclear ideas entered the story. One of the first steps upward was the nuclear thermal rocket. The idea is straightforward in principle. A reactor heats propellant, and that hot propellant rushes out the back to produce thrust. It is still a rocket, still using expelled mass to move forward, but it can reach higher exhaust speeds than ordinary chemical engines. That makes it a meaningful improvement. It offers a real gain. But even here, the stars remain distant. Nuclear thermal propulsion begins to stretch the limits of conventional travel, yet it still does not reach the realm where interstellar distance starts to feel human. It is a step upward, though not a leap across the gulf. Then the ideas became much bolder. Project Orion is one of the most dramatic concepts ever seriously considered for space travel. Its vision was almost shocking in its simplicity. Instead of relying on a steady engine, Orion imagined a spacecraft pushed forward by a series of nuclear explosions behind it. Each detonation would strike a massive pusher plate and drive the ship onward in pulses. It was an idea large enough to feel almost mythic, the kind of thing that sounds like it belongs to speculative fiction. Yet it was studied with real engineering seriousness. Orion mattered because it showed just how far human thought was willing to go once the stars entered the conversation. If ordinary rockets were too weak, then perhaps the answer was not refinement, but force on an entirely different scale. And yet Orion carried obvious burdens with it. It was physically bold, but politically and practically difficult. The idea of launching a ship by setting off nuclear devices behind it belongs to a world of immense risk, international tension, and environmental concern. Even if the physics could be made to work, the surrounding reality made the concept deeply hard to accept. Orion remains important partly because of what it says about the stage human imagination had reached. The moment interstellar distance became real, the ideas themselves became more severe. Beyond Orion, the thought of fusion kept returning. Fusion has a special place in this story because it promises the kind of energy density that interstellar travel seems to demand. It is the process that powers the stars themselves. That fact alone gives it an almost poetic gravity. If humanity ever wants to travel between suns, one natural instinct is to imitate. In some smaller controlled form, the energy source already burning inside the suns. Concepts such as Project Daedalus took this possibility seriously, imagining huge unmanned craft driven by fusion pulses and capable of reaching meaningful fractions of light speed. At that point, the conversation changes again. The trip is no longer measured only in thousands of years. It begins, at least on paper, to move toward decades. That is what all of these ideas reveal together. They show the point at which human imagination became serious. Chemical rockets had revealed their limits. Gravity assists had revealed the elegance and the smallness of borrowed motion. And once those truths settled in, the response was not to give up, but to begin searching for engines and fuels that belonged to a much harsher scale of thought. Nuclear thermal propulsion, Orion fusion studies, and even antimatter concepts all belong to that same deeper effort. They are signs that once the stars were treated as real destinations, the old categories of travel were no longer enough. And yet, among all these massive visions, one of the strangest ideas takes the opposite path entirely. Instead of building a larger ship with denser fuel and heavier machinery, perhaps the answer is to make the spacecraft so light that light itself can begin to carry it. Among all the heavy visions of interstellar travel, one of the strangest ideas is also one of the lightest. Instead of building a larger ship with denser fuel, thicker walls, and more powerful engines, this idea moves in the opposite direction. It asks whether the spacecraft could become so small and so light that the burden of carrying fuel might disappear almost entirely. And once that thought appears, another one follows close behind. If a craft is light enough, perhaps it does not need to be pushed by onboard fuel at all. Perhaps it could be pushed by light. The idea of riding light sounds ancient and almost poetic. It feels like something that belongs to imagination before it belongs to engineering. But in modern physics, light does carry momentum. It can exert pressure, tiny in ordinary conditions, but real. If a sail were made thin enough and reflective enough, and if a strong enough beam of light were aimed at it, that sail could be pushed forward through space. In that sense, a light sail is exactly what it sounds like. A sail for the vacuum, catching light instead of wind. This is where the idea becomes serious. One of the clearest modern versions is Breakthrough Starshot. The concept is not centered on a giant ship. It is centered on extremely small probes, gram-scale payloads attached to ultra-thin reflective sails. Instead of launching a heavy craft and asking it to carry its own energy source for decades, the plan is to leave the energy infrastructure behind on Earth. A vast laser array would fire from here, pushing the tiny sail to extraordinary speed early in the mission. Once the acceleration phase was over, the probe would coast across interstellar space with almost no onboard mass devoted to fuel. And this is where the numbers begin to feel almost unreal. The concept aims for speeds near 0.2 times the speed of light. That is about 20% of light speed, or roughly 160 million kilometers per hour. At that speed, the journey to the Alpha Centauri system could fall into the range of about 20 to 30 years. After so many severe numbers earlier in this story, this one lands differently. It belongs to a timescale that a human being can feel. It is still long. It still asks for patience. But it no longer belongs to deep civilizational time. It begins to live inside the span of a life. That is what makes this idea so powerful. It does not solve the interstellar problem by forcing a heavy ship to become unimaginably stronger. It solves it by changing the kind of thing being sent. The payload becomes tiny. The infrastructure becomes external. The ship becomes almost a seed of a spacecraft, rather than a vessel in the traditional sense. This changes the entire emotional shape of the mission. Instead of a grand arc pushing itself toward another sun, the first successful interstellar traveler may be something closer to an instrument, a chip, a sail, and a whisper of mass moving at enormous speed. There is something beautiful in that reversal. The stars once seemed to demand colossal machines, as though only something immense could cross such distance. But the light sail idea suggests that the first real crossing may belong to something almost delicate. Not fragile in a careless sense, but minimal, stripped down, nearly weightless by comparison with all earlier dreams of starflight. Of course, the simplicity is only on one side of the equation. The spacecraft may be tiny, but the system needed to launch it is immense. A concept like Starshot calls for an enormous laser array, extraordinary beam control, advanced materials, and a level of precision that pushes modern engineering into very demanding territory. The sail must survive acceleration, remain stable, and keep its orientation under intense pressure. The laser infrastructure itself would be one of the most ambitious technical systems humanity has ever built. So this is not a cheap or easy path. It is a different kind of difficulty. The burden shifts from the spacecraft to the launch system. Still, that shift may be exactly what makes the concept feel plausible in a way many older Starflight ideas do not. It works with a reality that has been growing for years. Electronics can shrink, sensors can shrink, cameras can shrink, computing can shrink. A probe no longer needs to be large to be capable. And if capability can be packed into something small enough, then the road to another star no longer has to begin with a ship in the old human sense. It can begin with a sail and a speck. That changes the meaning of possibility. The first successful mission to another star may not look like the great human images of exploration at all. It may arrive without crew, without landing, without slowing, and without anything like a ship as earlier generations imagined one. And that means success itself begins to change shape. Because reaching another star with a tiny probe is very different from arriving there as a civilization. A fast interstellar probe may reach another star without ever truly settling into it. That is one of the strangest parts of the whole idea. Arrival in the first age of Starflight may look less like reaching a place and more like passing through a moment. Once a probe becomes very small and very fast, the journey changes shape. The travel time begins to shrink towards something a human being can actually feel. A crossing that once belonged to tens of thousands of years can start to fall into decades. But that gift comes with its own price. Speed shortens the wait, yet it also shortens the encounter. The faster the probe moves, the less time it has to look, measure, and understand while it is actually there. That means the first successful mission to another star may not arrive in the way people usually imagine arrival. It may not slow into orbit. It may not circle the star for years. It may not descend into the atmosphere of a world, land gently, and begin sending home a long record of patient observation. A tiny laser-driven craft moving at a significant fraction of light speed, it would be far more likely to perform a flyby. It would rush through the target system, gather what it could, and continue onward into the dark. Its success would come from surviving the crossing and snatching a brief set of measurements at the far end. There is something humbling in that. For generations, human beings pictured exploration as something gradual. A ship arrives, it anchors, it lingers, it studies. The first interstellar success may look much less secure than that. It may resemble a glance more than a visit. The probe may have only a narrow window in which the destination is close enough, bright enough, and geometrically favorable enough to capture meaningful data. During that brief passage, every image, every sensor reading, every signal would matter. And yet even a glimpse could be extraordinary. After all, the first photographs of another star's planetary neighborhood, taken by a machine launched from Earth and sent across interstellar space, would mark a change in human history. Even a brief look would carry enormous weight. A few images, a few measurements of light, heat, magnetism, dust, or atmosphere, a few signs of what kinds of worlds circle another sun. These would be small returns in quantity and immense returns in meaning. The first interstellar mission may teach humanity not through abundance, but through rarity. That is part of why the idea feels so quiet and modern at the same time. The success would not be measured by conquest. It would not be measured by settlement or by the carrying of human life into a new home. It would be measured by whether a tiny instrument could cross the gulf, remain intact, and send back a moment of truth from a place no human being had ever touched. In that sense, the earliest form of star travel may belong more to observation than to arrival in the old human sense. And the deeper reason for that is simple. To slow down is hard. A probe accelerated to extreme speed can cross the interstellar gap much faster, but decelerating at the far end would demand another solution, just as powerful as the one that launched it. If the spacecraft is tiny, because that is what made acceleration possible, then carrying extra systems for braking becomes difficult. So the first interstellar traveler may have to accept a different kind of relationship with its destination. It may not enter and remain. It may pass and report. That gives the whole idea a strangely delicate quality. The mission becomes less like planting a flag and more like catching a signal in motion. The probe hurries toward another star for decades, only to experience its destination in a brief burst of closeness. Everything depends on that short interval. Everything depends on preparation made long before, on decisions fixed at launch, and on instruments small enough and resilient enough to do meaningful work in an instant. This does not make the mission lesser. It only makes it more honest. The first success between stars may be modest in form and enormous in consequence. It may not satisfy every old dream of arrival. It may not bring human beings into another system or create any sense of permanence there. But it would still represent something profound. It would mean that a machine from Earth crossed the deep dark, reached another sun, and saw something real there with our instruments and our curiosity carried inside it. That is a quieter form of exploration than people once imagined. But quiet forms of exploration still change the world. And once that image settles in, another question comes back into view with even greater force. If the first arrival is likely to belong to something tiny, fast, and almost weightless, what happens when human bodies are placed back into the story? A robotic probe asks for one thing above all else. It asks to survive. A human mission asks for far more. It asks for life to continue inside the vehicle. It asks for a small world to be carried through the dark. That difference changes everything. A tiny probe can be built around a narrow purpose. It can carry instruments, a power source, a communication system, and just enough structure to endure the trip. It does not need comfort. It does not need sleep. It does not need air, water, food, medicine, or emotional stability. It can be small because its purpose is small in one sense, even if the meaning of its mission is enormous. It only has to keep functioning long enough to observe, record, and send something home. The moment human beings enter the picture, the ship stops being only a machine. It becomes an environment. The vessel must carry air that can be breathed again and again. It must carry water that can be purified and reused. It must carry food, or some way of growing it, or some closed cycle capable of supporting life for years, decades, or longer. It must provide warmth, waste processing, medical care, sleep, and protection from mechanical failure. Every ordinary need of the human body, so easily met on Earth by a living planet, would have to be recreated inside an artificial structure moving through interstellar space. That alone would make the mission vastly harder than a robotic crossing. And then comes radiation. Earth protects life with a thick atmosphere and a magnetic field. Together, they soften the constant flow of energetic particles that move through space. Outside that protection, the human body becomes much more vulnerable. Over short missions, radiation is already a serious concern. Over a journey lasting decades, centuries, or longer, it becomes one of the central problems. A human starship would need substantial shielding, which means more mass, which means more difficulty accelerating the craft in the first place. The mission grows heavier as soon as it tries to become safer. That is the pattern that keeps returning. The stars punish complexity. The more human the mission becomes, the more the ship must carry. The more it carries, the harder it becomes to move at meaningful speed. A robotic probe can survive with extreme minimalism. A crewed mission cannot. It must become a habitat, and a habitat is always heavier than an instrument. Then there is the question of time inside the ship. A short journey is one thing. A multi-generational journey is something else entirely. If the trip lasts longer than a single human life, then the mission is no longer only about transport. It becomes about society. Children may be born on board. Entire lives may unfold within the vessel. The people who arrive may not be the people who departed. They may know Earth only through stories, recordings, education, rituals, and inherited memory. In that case, the ship is no longer simply carrying passengers. It is carrying a lineage. And with that comes another layer of difficulty. A human community must remain socially stable. It must handle conflict, grief, boredom, authority, purpose, and change. It must avoid collapse not just mechanically, but psychologically. A machine can endure silence. Human beings live inside meaning. They need reasons, relationships, continuity, and some way of preserving a shared sense of direction. On a journey that lasts generations, the mission would have to protect not only bodies, but culture. That is one reason human interstellar travel feels like a different category of thought from robotic exploration. A robotic mission can fail in simple ways. A component breaks, power fades, communication ends. A human mission can fail in all of those ways and more. It can fail biologically, socially, emotionally, ethically. The ship would need to remain a working world, not merely a working vehicle. Some imagined solutions try to escape that burden. Suspended animation is one idea. Embryo missions are another. Vast generationships appear again and again in human imagination. Each of these is an attempt to answer the same hard truth. Sending people to another star is not just harder than sending a probe. It may be harder by an entire order of meaning. A probe asks to cross the dark. A human mission asks to carry home with it. That is why the first real interstellar success is so likely to belong to machines rather than people. Not because human beings lack courage, but because biology is heavy. Life is demanding. A person is not an instrument that can simply be bolted into a hull and pointed outward. A person brings a living world of needs, and that living world must be sustained without interruption. Even if no human being is on board, another difficulty still waits quietly in the background. A journey lasting centuries or millennia does not only test life, it tests matter, circuits, memory, and time itself. Machines also grow old. That can be easy to forget when people imagine a spacecraft as something clean, sealed, and unchanging, moving through the dark with steady purpose. But a long journey does not leave a machine untouched. Time works on metal, electronics, memory, power systems, and structure. On Earth, aging often arrives with weather, moisture, heat, and friction. In deep space, it arrives differently. It arrives through silence, radiation, cold, long exposure, and the simple fact that anything built by human hands must keep existing far longer than it was ever meant to in ordinary life. A short mission can outrun some of these problems. A mission lasting centuries or millennia cannot. Even a robotic probe with no human needs on board is still a collection of parts. Wires can degrade, materials can fatigue, lubricants can evaporate or break down. Tiny flaws that do not matter at first can become serious over enough time. Computer systems can suffer errors. Memory can slowly fail. A spacecraft moving for decades may still feel durable. A spacecraft expected to cross interstellar distance at current speeds begins to feel fragile in a different way. The question is no longer whether it works at launch. The question is whether it can remain itself across ages. Power is one of the clearest examples. Many deep space probes rely on radioisotope power systems. These are extraordinary devices because they provide electricity far from the sun, where solar panels become less practical. They make missions like Voyager possible, but they do not last forever. Their power slowly declines as the radioactive material decays. That means a spacecraft can remain intact and still begin, piece by piece, to grow dimmer. Instruments are shut down. Systems are prioritized. The mission continues, but in a narrowing form. Over enough time, even a healthy spacecraft can become a quieter and quieter version of itself. Voyager gives this process a human scale. At launch, it had far more electrical power available than it does today. Decades later, engineers have had to manage that fading carefully, choosing which instruments remain alive and which must be turned off so the mission can continue a little longer. There is something moving in that. A spacecraft can still be traveling faithfully outward while, inside it, the small flame of usable power keeps shrinking. And power is only one part of the story. Space is not empty in the way people sometimes imagine. Over long spans, a craft is exposed to dust, tiny particles, radiation, and micrometeoroids. Any one impact may be small. Across enough time, the total risk grows. A mission lasting centuries would not need one dramatic collision to be endangered. It could be worn down by a long history of small encounters. The spacecraft keeps moving, but the environment is always touching it, however faintly. Navigation grows stranger too. A machine traveling for decades can still rely on a world that remembers where it is, how it was built, and what it is meant to do. Stretch that mission outward into centuries, and continuity itself becomes part of the engineering problem. Star positions shift slowly. Reference frames change. Communication becomes thin and delayed. A vehicle moving far from the sun also loses the comfort of familiar local guidance. It must increasingly carry its own stability with it. That is one reason redundancy matters so much in deep space design. Important systems may need backups. critical decisions may need fault tolerance. A spacecraft crossing interstellar distance cannot depend on quick rescue, real-time correction, or regular repair. It must survive by being patient, self-contained, and resistant to slow forms of failure. Even then, there is no guarantee. A probe can launch perfectly, travel beautifully, and still fail long before its target ever grows bright enough to see. That is what makes time such a quiet adversary. It does not always destroy suddenly. Often it subtracts. A little less power, a little more wear, a little more uncertainty, a little more strain carried forward year after year. Over a short mission, those losses can be managed. Over a very long one, they begin to define the mission itself. So even after propulsion, shielding, and guidance are imagined, another truth remains waiting in the dark. A spacecraft does not merely have to cross distance. It has to remain alive as a machine while it does so. And even if it survives all of that, one of the strangest parts of the journey would still be waiting at the far end. Seeing another star is one thing. Letting Earth know what was seen is another. A spacecraft can arrive long before Earth knows that it has arrived. That is one of the strangest parts of interstellar travel. In ordinary life, seeing and knowing often feel almost the same. A person reaches a place, and the fact of arrival is immediately real to everyone nearby. But across the distance to another star, arrival and awareness split apart. A probe may reach its destination, pass through a new system, gather images and measurements, and still leave Earth waiting in silence for years before any of that becomes known. The reason is simple and also severe. Nothing carrying information can outrun light. That means even the fastest possible message from Proxima Centauri would still need about 4.25 years to cross the gulf back to Earth. The probe might see something extraordinary in one moment, yet human beings on Earth would remain unaware of it for more than 4 more years. In that sense, the data must make a second journey after the spacecraft has already completed the first. That changes the emotional texture of discovery. A successful mission to another star would not end in a sudden shared moment of celebration. There would be no instant announcement the same day the probe arrived. No immediate confirmation. No quick correction if something went wrong. Instead, there would be delay, silence, and the long discipline of waiting. Earth would know where the craft was supposed to be. It might know when the encounter was expected to happen. But knowing that a moment should have occurred is not the same as receiving proof that it did. That gap matters because it adds another layer of distance to the story. The spacecraft is already separated from Earth by trillions of kilometers. Then knowledge itself becomes separated from events by years. A probe could fly past another star's world, capture images of its light, perhaps even glimpse the outline of a planet, and all of that would already belong to the past by the time the first signal reached home. In a very real sense, Earth would always be learning history. Even the freshest data would arrive already aged by light travel time. That also means control becomes thin and limited. Within the solar system, communication delays can already be frustrating. Commands take time, responses take time. But at interstellar distances, the lag grows so large that a probe must operate with extraordinary independence. Earth cannot guide each moment as it happens. It cannot watch in real time and adjust on the fly. If a critical observation window lasts minutes or hours, the spacecraft must handle it alone. the important choices would need to be prepared long in advance, built into software, timing, and mission design before the encounter ever began. So the mission becomes even quieter than it first seems. The probe would travel for years or decades, reach another star, and perform its most important work in solitude. Only later would the meaning of that work begin to unfold back on Earth. This gives interstellar discovery a different kind of rhythm from almost any earlier exploration. The event happens there. The understanding happens here. The two are joined, but never at once. And yet that delay does not make the achievement smaller. It may even deepen it. There is something powerful about the thought that human beings could send a machine so far away that even its message home must cross years of darkness to reach us. It makes the act of communication itself feel almost as grand as the act of travel. The data is no longer just information. It becomes a return, a signal carried back over light years, a patient answer from the edge of another sun. That return would have its own tension. Engineers and scientists would wait. The wider world would wait. A date on a calendar could mark when the first signal might arrive, but not what it would contain. The message might be clear. It might be weak. It might be incomplete. It might never come at all. The years of delay would gather uncertainty around every expectation. So even success would arrive slowly. A probe might survive the crossing, perform the flyby, and send its findings home. But Earth would receive that knowledge in fragments stretched across time. Discovery would feel less like a shout and more like a light gradually appearing far off in the dark. And once that delay is truly felt, another question begins to rise almost on its own. If a message from the nearest star would still spend more than 4 years on its way back, what kind of Earth would still be waiting when the first news finally arrived? The future feels different when it is measured in decades rather than millennia. A probe that arrived at the next star within something like a human lifetime would still belong to the future, but it would belong to a future that feels connected to us. Not close exactly, not familiar in every detail, but still part of the same long historical breath. The people waiting for the first message home might not be the same people who watched the launch, but they could still be their children or students, or the inheritors of institutions that remember why the mission began. That makes this version of the journey feel gentler. If a very fast probe left Earth in 2026 and reached the Proxima system a few decades later, the world receiving its data would already be changed. Technology would be different. Communication systems would likely be faster, smaller, more embedded in daily life, perhaps less visible and more ambient than they are now. Artificial intelligence could be woven far more deeply into education, research, governance, and ordinary conversation. Energy systems might shift. New materials might exist. Spaceflight itself could feel more normal, more commercial, or perhaps more politically contested than it does today. Some things that feel advanced now may seem awkward and early by then, the way older computers or early satellites seem to us. Politics would likely shift too. Even a few decades can redraw the mood of the world. Alliances change, priorities change. Nations rise in confidence or slip into uncertainty. New tensions appear. Old ones fade. A mission launched in one political atmosphere might be received in another entirely. What begins as a scientific act in one era might later be seen as a symbol of cooperation, a relic of rivalry, a monument to ambition, or a quiet turning point that only became fully meaningful with time. Culture would change along with it. The stories people tell about the mission would not stay fixed. The generation that launched it might speak in the language of daring, first steps, and technological possibility. The generation receiving the first data might understand it differently. To them, the mission could feel less like a gamble and more like a long-promised inheritance finally arriving. Or it might seem like a message from an earlier age, shaped by hopes and assumptions that no longer feel entirely their own. The same event can change meaning as the world around it changes. That is one of the quiet truths of long projects. The people who begin them do not get to control how they will finally be understood. They can build carefully, explain clearly, and preserve their intentions as best they can. But time always adds its own interpretation. A probe reaching another star a few decades from now would still be carrying instruments and code from one moment in history into another moment that may already see the universe differently. And yet, there is something beautiful in that distance, because even a changed Earth would still be able to feel the continuity. The launch would not yet belong to myth. Records would survive, images would survive, speeches, plans, diagrams, debates, and memories would survive. There would still be people alive who remembered the early excitement, or who had been taught by those who did. The mission would feel old, but not ancient. Its return would still be able to touch something living in collective memory. That matters because it changes the emotional tone of the message home. The first data from another star would not arrive to a blank world. It would arrive to a civilization already shaped, in some small way, by the expectation of that moment. Children might have grown up hearing about the mission in school. Scientists might have spent careers preparing for the signal. Artists, writers, and filmmakers might have imagined the arrival for decades before it happened. The return of the data would not only tell humanity something new about another star, it would also complete a long arc of waiting within human culture itself. Still, even this gentler version of the future would not be simple. A few decades are enough to change standards, values, and assumptions. The people receiving the message might interpret the mission with more caution, more reverence, more indifference, or more wonder than the people who launched it. They might see it as a beginning rather than a climax. They might immediately ask what comes next. A faster probe, a larger one, a braking mission, a mission aimed not just to pass through, but to remain. So even the short version of interstellar time still teaches the same lesson. The future does not wait in stillness for a spacecraft to arrive. It keeps moving. It keeps changing. It keeps becoming something else while the probe is on its way. But this is the softer version of that truth. The same question becomes far stranger once the travel time no longer spans decades, but thousands or tens of thousands of years. A very long interstellar mission would leave one Earth and report back to another, so distant in time that the word same begins to lose its meaning. When the travel time stretches into thousands of years, the question changes in a very deep way. A probe is no longer just crossing space. It is crossing historical eras. It is leaving one human world and moving toward a future human world that may be connected to us by ancestry, by biology, by memory, or perhaps only by fragments. The launch and the arrival would no longer belong to the same civilization in any ordinary sense. That is difficult to feel at first, because people are used to history as something written down in books, divided into neat periods, made to seem stable from a distance. But real human history is movement. Languages drift, borders dissolve, religions divide and reform, institutions rise, harden, and fade. Entire ways of seeing the world can feel permanent for a while, then later become strange and remote. The longer the span, the less safe it becomes to assume continuity. A probe launched in 2026 at the kinds of speeds humanity can really achieve now could take thousands or even tens of thousands of years to reach the nearest star. That means the culture that launched it might not merely change, it might vanish. Its languages could evolve beyond recognition. Its political systems could disappear. Its conflicts could become obscure. Its values could be remembered imperfectly, if at all. The countries involved in the launch might survive only as names in old records, or as archaeological categories, or perhaps not even that. The mission itself might pass through ages in which no one remembers why it was launched, followed later by ages that rediscover it and reinterpret it entirely. That is one of the most haunting possibilities in the whole question. A spacecraft could travel faithfully outward, while the civilization that built it becomes ancient long before the destination is reached. The machine continues. The originating world does not. In that sense, the probe becomes a message carried forward not only across distance, but across disappearance. It is no longer simply an instrument sent from Earth to another star. It becomes a surviving thread from one age of humanity to another. And threads can become very thin over long spans. Even if human beings remain on Earth throughout all those millennia, there is no guarantee that memory remains unbroken. Archives can be lost. Knowledge can narrow. Priorities can shift away from long missions toward immediate crises or entirely different visions of life. A project that once felt noble may later feel irrelevant. A world focused on survival may not care about a probe drifting between stars. A world transformed by abundance may view it as a quaint, early effort from a technologically immature age. Either way, the original meaning of the launch could become hard to preserve. This is where interstellar travel begins to reveal something about human impermanence. People often imagine the challenge as purely mechanical. Build a stronger engine, build a more durable craft, give it time. But a journey lasting thousands of years quietly asks a second question underneath the first. What remains of us across that kind of time? Not just our machines, but our languages, our institutions, our emotional continuity, our ability to remember what mattered to those who came before us. A mission of that length becomes almost archaeological before it is complete. The probe would not simply be awaited, it would be inherited again and again. Each generation that remained aware of it would receive it from the previous one as an unfinished story. They would decide whether to keep caring, whether to keep tracking it, whether to keep preserving the meaning of its voyage. In that way, the mission would say as much about Earth as it says about the stars. It would become a test of whether a civilization can keep hold of something larger than a single age. And if the line of memory ever broke, the mission would still continue outward regardless. That may be the strangest part of all. The spacecraft does not need human attention to keep moving. It obeys physics, not remembrance. So it could cross the dark while empires fall, coastlines shift, species vanish, and entirely new human worlds come into being beneath it. The silence around it might deepen, not because it had failed, but because history had moved on. That is why interstellar travel, at current speeds, begins to feel like a study of impermanence as much as distance. It reminds us that reaching another star is not only about whether a machine can survive the crossing. It is also about whether anything recognizably human can endure alongside the meaning of that crossing. And once that truth settles in, the journey begins to ask something even deeper. Why do human beings begin projects whose ending they know they will never personally see? There is something deeply human about beginning a task that extends beyond one lifetime. Human beings have always done this. A cathedral rises stone by stone across generations. An observatory is built so that people not yet born can look farther than the builders ever could. Archives are preserved in the hope that memory will survive those who first gathered it. In each case, the beginning is real, even when the ending belongs to someone else. That same pattern lives inside the idea of sending something toward another star. In that sense, interstellar travel does not stand completely apart from the rest of human history. It is an extreme version of something older. People often imagine great efforts as personal achievements, as if the purpose of beginning must always be tied to seeing the result with one's own eyes. But much of civilization was built through a different logic. Many of the most meaningful things human beings have made were started by people who knew they would not live to see the finished form. They began anyway. They gave labor, vision, care, and belief to something that would only fully belong to the future. That changes how a mission to another star can be understood. If a probe leaves Earth knowing that arrival may happen long after the launch generation is gone, the mission stops looking like an ordinary expedition and starts looking more like a continuity project. It becomes less about possession and more about inheritance. The people who begin it are not claiming the destination for themselves. They are placing a thread into time and trusting that others may one day hold the far end of it. There is something quiet and serious in that kind of trust. To begin a journey you will never finish is an act of faith, though not necessarily in a religious sense. It is faith in continuity. Faith that some form of human care, or at least human curiosity, will still exist later. Faith that the future is worth speaking to, even if it answers in a language you do not know. That is part of what gives long projects their emotional dignity. They are not only practical works. They are statements about what a civilization believes is worth carrying forward. A star mission belongs to that tradition. It says that knowledge matters enough to begin even when completion is distant. It says that curiosity is not only a private feeling, but something that can be inherited. It says that one generation can offer another more than comfort or warning. It can also offer an unfinished question, an outward motion, a widening of the horizon. That is why missions like this begin to feel different once the timescale is fully understood. They are no longer about speed alone. They are about character. What kind of species starts something this large? What kind of civilization decides that the answer to deep distance is not silence, but the patient sending of a machine into the dark? What kind of mind looks at a journey longer than a lifetime and still says begin? There is an answer hidden in the history of human making. People plant trees whose shade they will never sit in. They preserve books they will never reread. They build institutions meant to protect knowledge after they are gone. They create art for unknown viewers. They leave maps formulas, stories, and buildings behind. Again and again, human beings act as though the future is real enough to receive gifts from the present. A star mission is one of the farthest reaching versions of that same habit. And that is why it feels so moving. Because the launch would not merely be a technical act, it would be an offering. A way of saying that the chain of human attention should extend beyond immediate need, beyond one generation's lifespan, beyond the narrow span of personal reward. It would treat curiosity as something larger than the self and larger than the present moment. The mission then becomes a kind of trust placed in time, not trust that everything will remain the same. History gives no reason to believe that. Not trust that the future will think exactly as we do. It will not. But trust that some future, in some form, may still be there to receive what was begun. Trust that memory, knowledge, or wonder might survive long enough for a message sent outward to still mean something when it finally comes back. This is one reason the idea of interstellar travel stays with people even when the numbers are severe. It speaks to something old in human life. The desire not only to survive, but to continue. Not only to know, but to hand knowledge onward. Not only to live within one age, but to contribute to a story that extends beyond it. And near the end of that thought, another strange idea begins to appear. Starting first is not always the same thing as arriving first. Sometimes a journey begun with courage may still be overtaken by one begun much later, with tools not yet invented. A mission launched early feels brave. There is something stirring about the thought of beginning now, with the tools already in human hands, even if those tools are still primitive by interstellar standards. A spacecraft leaving in 2026 would carry a certain honesty with it. It would say that waiting forever is also a kind of decision, and that sometimes the desire to begin matters enough to accept slowness. But across distances this large, another thought begins to appear, and it changes the shape of the story. Leaving first may not mean arriving first. This is the strange logic sometimes called the weight calculation. The idea is simple in outline. If a probe launched now travels slowly enough, and if future civilizations later build much faster propulsion, then a second mission launched centuries afterward could overtake the first and reach the same star sooner. In that case, the earlier launch would still have begun the journey first, but it would not be the first to arrive. That thought feels almost backwards at first. Human beings are used to treating early departure as an advantage. In most ordinary travel, the person who leaves first gets there first. But the stars introduce a different kind of arithmetic. The distance is so vast that improvements in speed can outweigh centuries of delay. A mission launched with much better propulsion can erase the head start of a slower craft simply because the crossing is long enough for speed to dominate everything else. This gives patience a new kind of dignity. A civilization might look at current spacecraft speeds and decide that beginning immediately would create a journey so long that later technology would almost certainly surpass it. In that case, waiting would not be laziness. It would be strategy. It would mean accepting that some destinations punish haste and reward better tools. 1,000 years from now, if propulsion has changed deeply enough, the trip to the nearest star could be vastly faster than anything possible today. That is not a certainty, but it is a reasonable possibility. And yet, the thought cuts both ways. If everyone waits for a better age, no one begins. Every generation could imagine that the next one will be more ready, more capable, more deserving of the first real attempt. In that way, the logic of waiting can become endless. A mission delayed for better technology might always find another reason to delay once more. So the question becomes philosophical as much as technical. At what point is the future good enough? At what point does patience stop being wisdom and start becoming postponement? That is why this idea feels so powerful near the end of the journey. It does not simply tell us something about propulsion. It tells us something about how human beings relate to time. One generation may choose to begin badly rather than wait perfectly. Another may choose to wait, trusting that a later launch will carry more meaning because it will have a real chance of arriving within a human frame of understanding. Neither impulse is foolish. One honors courage, the other honors proportion. And together, they reveal one of the deepest truths in the whole question. The nearest star is so far away that even the decision of when to leave becomes part of the mystery. On Earth, travel usually begins with motion. Between stars, travel may begin with deciding whether motion now is truly wiser than motion later. Now the question can finally be answered clearly. If we left in 2026 and aimed for the nearest star beyond the Sun, the answer depends entirely on what kind of machine we are imagining. And that is why the question opens into something much larger than it first appears. The destination is Proxima Centauri, about 4.25 light years away. That makes it the nearest star beyond the Sun, and still far enough to turn travel into an encounter with time itself. If the journey were measured by a spacecraft like Voyager 1, moving outward at about 17 kilometers per second, the trip would take roughly 73,000 years. That is the first hard answer. It is honest, real, and severe. It means that with the kind of outward speed humanity has actually achieved in deep space, the next star is reachable only on timescales far larger than civilization, as we usually imagine it. If the journey were measured by the fastest speed any human spacecraft has ever reached, using Parker Solar Probe's peak speed of about 700,000 kilometers per hour, or 191 kilometers per second, the answer becomes smaller, but still immense. Even if that speed could somehow be sustained all the way through interstellar space, the trip would still take about 6,700 years. That is a dramatic improvement, but it still belongs to deep historical time, not to ordinary human expectation. Only when the conversation turns toward much more advanced ideas does the timescale begin to change in a truly startling way. Light sail concepts such as Starshot imagine tiny probes pushed to around 20% of the speed of light. At those speeds, the crossing could fall into the range of about 20 to 30 years. Suddenly, the journey moves out of the realm of prehistory and into something like a human lifetime. But it does so by changing the mission completely. The payload becomes tiny, the encounter becomes brief, arrival becomes more like a passing look than a settled presence. So the real answer comes in layers. At present-day outward spacecraft speeds, the trip takes tens of thousands of years. At the most extreme speeds ever briefly reached by a human machine, it still takes thousands. Only under advanced concepts that do not yet exist as working interstellar missions does the trip shrink into decades. That is what makes the nearest star such a powerful destination in the human mind. It is close enough to be named, measured, and imagined. Yet it is far enough to humble every ordinary instinct about movement. It forces a person to see that another star is neither fantasy nor intimacy. It is real, and its reality is vast. Humanity can begin that journey now. In one sense, it already has, through the outward motion of its probes and the seriousness of its ideas. But current technology still cannot make the next star feel near in the lived human sense. It can only make the crossing conceivable. That may sound small, yet it is not small at all. To make another sun conceivable is already one of the great expansions of human thought. So the answer to the title is both simple and enormous. If we left in 2026, reaching the next star could mean a few decades, or thousands of years, or more than 70,000, depending on what kind of future we are able to build into the vehicle. And in every version, the same truth remains waiting beneath the numbers. The sky looks full every night, but the road to the next star is made of distance, time, and the long memory of human curiosity.